A game that was popular in the 1970s was a game called Merlin. It was an electronic game with a grid of 9 lights, each of which could be either on or off. Pressing a light would toggle its state and the state of some of the lights around it, turning lights on if they were off, and turning them off if they were on. And which lights were toggled depended on which light was pressed. Only buttons 1 to 9 were used in this game. They sit in a 3x3 grid. The object of the game was to reach a specified final configuration of lights from a given starting configuration. Now, Merlin was similar to another game, more recent game called Lights Out, popular in the 1990s. Lights Out was played on a 5x5 grid of lights, and pressing a light would toggle that light as well as some of the lights around it. And the object of that game was to get all the lights off, hence the name. Now, there are lots of questions you could ask about such games. For instance, is a solution always possible, no matter what configuration you start in? Are there multiple solutions? And how do you find a solution? Now, these questions I've just asked sound a lot like questions we might ask in linear algebra, and the similarity doesn't end there. We can keep track of lights in a mathematical fashion by using a number system with only 2 numbers, 0 and 1, using 0 if a light is off and 1 if it is on. Then a configuration of lights can be recorded as a vector of zeros and ones. In the game of Merlin, this would be a 9-dimensional vector of zeros and ones. The arithmetic of these vectors relies on the arithmetic of toggling lights, which we'll now describe. If we imagine pressing a button as adding 1, then we'll want 1 plus 1 to equal 0, since toggling a light that's on will turn it off. Similarly, we want 0 plus 1 to equal 1, since toggling an off light will turn it on. You might also notice that not pressing a button does nothing to a light. So 1 plus 0 equals 1, and 0 plus 0 equals 0. This produces an addition table, sometimes called addition mod 2, since you can think of these numbers as remainders of integers when you divide by 2. And addition is basically just keeping track of how even and odd numbers behave, if you think of 0 as even and 1 as odd. Okay, now that we have an arithmetic of addition mod 2, let's return to the game. Pressing a button toggles that light and some of the lights around it. The rules of that were specific to Merlin and are not so important right now. What is worth noting is that each button corresponds to a vector, vi, of zeros and ones that indicate which lights will get toggled if you press button I. If pressing button 3 toggles lights 2, 3, 5, and 6, that means we'll let v sub 3 be a vector with 1s in positions 2, 3, 5, and 6, and zeros everywhere else. So then v3 would be the vector with 9 entries, 0, 1, 1, 0, 1, 1, 0, 0, 0. In the same way, we can find for every other button a vector v sub I that corresponds to pressing button I. We can also let v be a vector of zeros and ones representing the starting state of lights. And if you add v sub I to that vector, you will get a vector representing the new configuration of lights on the board after pressing button I. So, if you start in configuration represented by vector v, and then press button 3, button 4, then button 3, you can use the sum v plus v3 plus v4 plus v3 to determine their final configuration. So pressing buttons is just like doing vector addition mod 2. Once you realize this, you can easily see that because addition is commutative, notice that the order of addition mod 2 doesn't matter, then the order of addition of vectors doesn't matter either. So the final configuration can be expressed v plus v3 plus v3 plus v4. Now you might be tempted to express this as v plus 2 times v3 plus v4. But we should notice another thing, that 2 times v3 means to add v3 twice. But that's the same as doing nothing, because you're just toggling some collection of lights associated with button 3 twice in a row, which is the same as doing nothing. So this is the same as v plus v4. So for any feasible configuration, you only ever have to press a button one time or no times. This suggests a times table, mod 2, that 0 times any number is 0, and 1 times any number is that number. So now this unusual number system with just 2 numbers has both an addition and a multiplication. This number system has a name. It's called the finite field of order 2, but you don't really need to know that. Pressing a number of different buttons is then the same as taking linear combination of button vectors and adding that to the initial configuration to produce a final configuration. As we've noted, you never have to press a button more than once because pressing a button twice returns the configuration to its original state, and the order of addition of these vectors doesn't matter. So if I want to find which buttons to press to get from the initial configuration, let's call it v sub initial, to the final configuration, v sub final, then I am looking for a linear combination of button vectors v sub I that have only 0 or 1 as coefficients in the combination, and which add up to the difference v sub final minus v sub initial. We can use the fundamental correspondence to write this as a matrix equation. Let M be the matrix whose columns are the button vectors v sub 1 through v sub 9. And let X be the vector with components x sub I, the vector of 0 and 1 coefficients indicating which buttons should get pressed to get from the initial to the final configuration. Then, given v final minus v initial, I'm trying to solve M times X equals v final minus v initial for X. And now we see that answering the 3 questions is the same as answering similar questions about solutions to mx equals b. For instance, is a solution always possible no matter what configuration you start in? Are there multiple solutions? And how do you find a solution? These are really linear algebra questions. In the last lecture, we looked at the concept of an inverse of a matrix. And we saw that for a system of equations, Ax equals b, if the matrix A has an inverse, then the system can be solved by multiplying on both sides by A inverse on the left. Then we find x equals A inverse times b. In practice, solving a system in this way is not the preferred method because we must first find the inverse of A, and doing that involves row reduction. We'll discuss how to do that in this lecture, but suffice it to say it's not faster than doing Gaussian elimination on the system of equations. So why do we care so much about the inverse of a matrix? Well, for one reason, the inverse might have a specific meaning, just as the stiffness matrix is the inverse of the flexibility matrix for masses hung on a flexible beam, as we discussed in the last lecture. Also, understanding the inverse of a matrix A gives us insight into the nature of the linear transformation that's represented by matrix multiplication by A. And it also gives insights into the nature of solutions to the linear system Ax equals b. We've already seen some examples. For instance, we know that a linear system like Ax equals b either has no solutions, one solution, or infinitely many solutions. However, if A has an inverse, we saw last time that AX equals B must have a single unique solution, because in that case, X equals A inverse times B, and we know A inverse is unique, and B is specified in the problem. What we shall see this time is that if AX equals B has a single unique solution for every B, then A must be an invertible matrix. So this property of AX equals B having a unique solution for every B is actually equivalent to A being invertible. In fact, in this lecture we will learn many more examples of criteria that are equivalent to A being invertible. And we can use these insights to answer the questions raised by the games of Merlin and Lights Out. Let's begin by addressing the question of how to find an arbitrary n by n matrix inverse. We've already seen a formula for 1 by 1 and 2 by 2 matrices. For any n by n matrix, I could attempt to give you a formula, but in practice, no one really remembers the formula for larger than 2 by 2 matrices. Instead, I will show you a procedure for finding one. This procedure rests on the interesting fact that any elementary row operation on a matrix can be represented as left multiplication by some matrix, called an elementary matrix. Here's what I mean. Let's say you have a 2 by 2 matrix A and you want to swap the rows, but all you have is a machine that can multiply the matrix A by another matrix. Well then, if you left multiply A by the elementary matrix E with entries 0, 1, 1, 0, you will see that this does indeed swap the two rows of A. Let's try this in an example. Carry out this multiplication of the matrix 0, 1, 1, 0 on the matrix 1, 2, 3, 4, and see what you get. You should see that the rows of the product are 3, 4, 1, 2, and these are the same as the rows of the other matrix, 1, 2, 3, 4, but switched. Similarly, the row operation of adding twice the second row to the first row also has a matrix that represents it. If you multiply the matrix 1, 2, 0, 1 times the matrix 1, 2, 3, 4, that will perform the row operation of adding twice the second row of 1, 2, 3, 4 to the first row of 1, 2, 3, 4. Check it yourself. You should get 7, 10, 3, 4. The second row is unchanged. The first row is now the original row, 1, 2, plus 2 times the second row, 3, 4, as I claimed. Now, how do we find the elementary matrix that accomplishes a given row operation by left multiplication? It's actually pretty easy. Just perform that row operation on the identity matrix, and then you will have the matrix E. In the examples that we just did, 0, 1, 1, 0 is what you get when you swap the rows of the 2 by 2 identity matrix. And 1, 2, 0, 1 is what you get when you take the 2 by 2 identity matrix and add twice the second row to the first. One fact to note now, because we'll use it later, is the following theorem. Elementary matrices are invertible. Well, why is this true? Well, if you think about it, it follows from the fact that row operations can be undone by another row operation. So if you have an elementary matrix E corresponding to a row operation R, and the row operation R prime is the one that undoes R, then look at the elementary matrix E prime corresponding to R prime. The product of E prime and E must be the identity matrix, because doing both row operations R and R prime leave the original matrix unchanged. So E prime is the inverse of E, and therefore E is invertible. And that's what we wanted to show. Okay, so now here's how we can find the inverse of an n by n matrix. First of all, remember a theorem we proved last time. If A is invertible, then AX equals 0 has only the trivial solution. This means that there are no free variables among the coordinates of the unknown vector x. So when you try to put A in reduced row echelon form, Because A is square, you have to get the identity matrix. Thus, an invertible matrix must be row reducible to the identity. Now, if we can row reduce the matrix A to the identity, then there's a sequence of row operations that will get us there. This is the same as successively multiplying the matrix A on the left by some elementary matrices, E1, E2 through, let's say, EK, to get to the identity matrix. Thus, the product of EK through E1 inverts A. Because inverses are unique if they exist, this product must be A inverse. And so this discussion points to a way to find the inverse of an n by n matrix A. We'll just form an augmented matrix by putting the matrix A on the left side and the n by n identity matrix on the right side of the augmented matrix. Then we will perform elementary row operations on the augmented matrix. This will, in effect, be performing multiplication of the elementary matrices on the augmented matrix. And the goal is to put the left side in reduced row echelon form, and if A is invertible, this will be the identity matrix. If we can do that, then the right side will be the product of those elementary matrices, because they must be the product of the elementary matrices with the identity. So the right-hand side has to be the inverse of A by the time you're done with this procedure. And this shows us a way to find the inverse of a matrix. Let's do an example. Suppose we want to use this method to invert the matrix A with entries 2, 7, 1, 4. Yeah, I know, we already have a formula for 2 by 2 matrices, but let's just use this example to see how the method works. First, we augment the matrix with the identity on the right-hand side, like this. Then we take this augmented matrix and try to row reduce the left side to get the identity matrix. If we can do this, A will be invertible. So, swapping rows, we get this. Now let's subtract twice the first row from the second, and we get this. Now let's multiply the second row by a -1. Then, subtract 4 times the second row from the first. Now we've gotten the left side to the identity. Therefore, the right side must be A inverse. And indeed, if you recall the 2 by 2 formula for inverses, it gives exactly this matrix as we verified in an earlier lecture. Now, inverting a 3 by 3 or an n by n with this method may be tedious, but the point is, if you've already programmed a computer to do Gaussian elimination, then computing inverses is easy. You may be wondering at this point, what if I cannot row reduce the matrix to the identity matrix? Does that necessarily mean that the matrix is not invertible? The answer is, as we shall now see, yes. So far, we have seen that if a matrix is invertible, it has several consequences. First, AX equals B must have a unique solution for any B. Second, AX equals 0 must have only the trivial solution. Third, the reduced row echelon form of A must be the identity. Now, I claim that in fact each of these criteria actually imply that the matrix A must be invertible. In other words, an invertible matrix is characterized by these criteria. In fact, there are a whole host of criteria that are equivalent to a matrix being invertible, that tie together many of the concepts that we've introduced so far. This is such a fundamental theorem about invertibility. Let's call it the fundamental theorem of invertible matrices. It's a really important theorem in the subject of linear algebra. And it says this: let A be an n by n square matrix. Then the following are equivalent. Number 1, A is invertible. Number 2, AX equals B has at least one solution for each B. Number 3, Ax equals 0 has only the trivial solution, x equals 0. Number 4, the reduced row echelon form of A is the identity matrix. Number 5, A is the product of elementary matrices. Number 6, the columns of A span Rn. Number 7, the columns of A are linearly independent. Number 8, the columns of A form a basis for Rn. Number 9, the rank of A is n. Number 10, the nullity of A is 0. Number 11, A transpose is invertible. Number 12, the rows of A span Rn. Number 13, the rows of A are linearly independent. Number 14, the rows of A form a basis for Rn. That's the theorem. And what we're saying is all these statements are equivalent. We're going to try to prove this. There are many pieces to this proof, and I don't expect that you'll be able to follow all the pieces just by listening to the proof once. So you might want to pause the video after we show each step and think about what we just discussed. To say that these statements are equivalent means that any of them must imply any of the others. But to show this, we don't have to show every single implication. It's enough for us to show a network of implications in which there's a path of implications that go from any statement to any other statement. So for instance, if we show that statement 1 implies statement 2, that statement 2 implies statement 4, that 4 implies 5 and 5 implies 1, then this will show that each of the statements 1, 2, 4, and 5 are equivalent because there is a chain of implications from any statement to any other statement. So we'll do this first. We've already proved that 1 implies 2, but I'll remind you of that argument here. If A is invertible, which is statement 1, then by multiplying both sides of Ax equals b on the left by A inverse, we'll get x equals A inverse times b. Thus, Ax equals b has at least one solution, which is statement 2. And statement 2 implies statement 4, because recall that if Ax equals b always has at least one solution, then Ax equals b never has any inconsistency, no matter what b is. So the reduced row echelon form of A cannot have a row of zeros in it. And since A is square, each column of the reduced row echelon form of A must have a leading 1 in it. So the reduced row echelon form of A must be the identity matrix. Before going further, let me point out that the square nature of the matrix A is important here. The theorem, and in particular this implication, isn't going to be true if A isn't square. Now, why does statement 4 imply statement 5? Well, we've already seen that if the reduced row echelon form of A is the identity matrix, then there's a sequence of elementary row operations that take A to the identity. These are represented by elementary matrices. So, A inverse is the product of elementary matrices. But we've seen that every elementary matrix is invertible because its inverse is just another elementary matrix corresponding to the row operation that undoes the original row operation. So A inverse is the product of invertible matrices. But then the inverse of A inverse, which is A, must be the product in reverse order of the inverses of those elementary matrices. And those inverses are also elementary. So A is also the product of elementary matrices. Now we have just one final implication, showing that 5 implies 1. But if A is the product of elementary matrices, and they're invertible, so A is the product of invertible matrices. By an earlier theorem, this means A is invertible too. We've thus completed our circle of implications, which shows all 4 statements, 1, 2, 4, and 5, in this theorem are equivalent. Now we can also show that 1 implies 3 implies 4. Note that this would mean that 3 is equivalent to each of the statements 1, 2, 4, and 5, because there is a path from 3 to each of those statements through 4. And there is a path to 3 from each of those statements through 1. So to see why 1 implies 3, note that if A is invertible, then you can multiply both sides of AX equals 0 by A inverse, and you will see that X necessarily has to be A inverse times 0, which is the 0 vector. Thus, x equals a 0 vector is the only solution to AX equals 0, and that's statement 3. By the way, it's good to note that statement 3 can be said another way if you recall what a null space of A is. It's a set of vectors that get sent to 0 by A. Then statement 3 can be rephrased as saying that the null space of A is trivial. It only has a 0 vector inside it. And now to see why statement 3 implies statement 4, note that if AX equals 0 has only the trivial solution, then there must not be any free variables, which implies that the reduced row echelon form of A must have a leading 1 in every column. Since A is square, the reduced row echelon form of A must be the identity. We've now shown everything in this picture is equivalent. Now we'll add a few more statements to the mix and show they too are equivalent to the matrix A being invertible. We can use a fundamental correspondence between a vector equation and a matrix equation to show that statement 2 is equivalent to statement 6 and 3 is equivalent to statement 7. Let's think about that for just a second. To say AX equals B is always solvable for each B is to say that a linear combination of the columns of A can produce any vector B. That's the same as saying the columns of A span all of Rn. Similarly, to say AX equals 0 has only the trivial solution is to say that the only linear combination of the columns that produce a 0 vector is one where all the coefficients are 0. That's precisely saying the columns of A are linearly independent. Finally, let's throw in a few more statements. Statement 8, that says that the columns of A form a basis for Rn, clearly implies both of the statements 6 and 7, because what it means to be a basis is that the columns are linearly independent and span Rn. In the reverse direction, we've already shown that statements 6 and 7 are equivalent as long as the matrix A is square. But then together they imply statement 8. So, statement 8 is equivalent to A being invertible. Statement 9, that the rank of A is n, is exactly what it means for the reduced row echelon form of A to have a leading 1 in every column. And that is equivalent to the reduced row echelon form of A being the identity. And by the rank nullity theorem, statement 9 is equivalent to statement 10, that the nullity of A, which is the dimension of the null space, is 0. By the way, you could also see statement 10 as equivalent to the statement that the null space of A is trivial, which is equivalent to the statement 3 that AX equals 0 has only the trivial solution. To show statement 11 belongs in this list of equivalencies, we'll first show that A inverse transpose is A transpose inverse. And this can be seen by taking A times A inverse equals the identity, and then taking that equation and taking the transpose of both sides. The transpose of the identity is the identity. Then A inverse transpose times A transpose equals the identity. So if A is invertible, then this equation shows that A transpose is invertible, which is statement 11. The reverse conclusion also holds by switching the roles of A and A transpose. Once we have statement 11, from that we see that any statement about columns has a corresponding equivalent statement for rows, which shows statements 12 through 14 are in the collection of equivalencies 2. And that shows the equivalencies of everything on the list in the invertible matrix theorem. The invertible matrix theorem is an amazing theorem it shows that the concept of invertibility is an important one because there's so many different ways to characterize it. For instance, look at this matrix, let's call it A. You might ask if it is invertible. Now we have lots of ways to decide because of the invertible matrix theorem. Perhaps if you visualize the column vectors in 3 dimensions, you could see that they span R3. Then you would know that the matrix is invertible. Immediately you would know lots of other things, that the row vectors must also span R3 and be linearly independent, that the reduced row echelon form of this matrix is the identity, that AX equals 0 has only one solution, that AX equals B always has at least one solution, and many other statements. So now let's return to the game of Merlin. We'd ask the following questions. Is a solution always possible, no matter what configuration you start in? Are there multiple solutions? And how do you find a solution? And now we'll be able to answer these questions because linear algebra shows us that finding a solution is equivalent to finding a vector x of zeros and ones such that mx equals v final minus v initial. Remember, m is a vector whose columns are vectors associated with pressing buttons. So the 3 questions become, does mx equals b have a solution for any b? Does mx equals b have multiple solutions for a particular b? And how do you find a solution? Now, according to the invertible matrix theorem, the first question is equivalent to the question, is M invertible? If it is, then the answer to question 1 is yes. There is always a solution no matter what configuration you start in or what ending configuration you desire. If it's not, then there will be some vectors b for which mx equals b is not solvable. Let's see what actually is the case with Merlin. The rules of Merlin say that if you press the center button, then all buttons in a cross get toggled. If you press a side button, all the buttons along that side are toggled. And if you press a corner button, then all 4 buttons in that corner get toggled. This produces 9 buttons, and if you write their vectors as columns in a matrix M and use arithmetic in a finite field of order 2, you can check that M row reduces to the identity matrix. So, by the invertible matrix theorem, M must be invertible. So there is always a set of buttons that can be pressed to take any configuration of Merlin to any other configuration of Merlin. And if M is invertible, the invertible matrix theorem tells us that there is a unique solution to mx equals b. So the answer to the second question is that there must be a unique choice of buttons to press that will get you to the desired configuration. Then, to find such a solution, you could use row reduction to solve mx equals v final minus v initial, and the entries of the vector x would give the coefficients needed to tell us what buttons to press. You might now have fun answering similar questions for the game Lights Out. For specific games like Merlin or Lights Out, there are ways to solve for x without doing much computation. See the references in the guidebook to learn more. But the key idea here is that we learned a lot about the solution by knowing some linear algebra.